Okay, so I'm going to talk a bit now about how I would simulate these systems, and what does a system look like which has some pulse shaping in it and then has transmission over a channel and reception in a sampling receiver. So this would be a typical diagram of how you would simulate such a system. You would put in Dirac functions, these are just your bits, 0 and 1 bits, would go into a transmitting filter, and the role of this filter is to shape the pulse to the desired shape. So we would choose the impulse response of this filter to be equal to the pulse shape that we want to achieve. After the transmission of the pulse train, it would go through a channel which introduces noise, go into a receiver that filters in some way or other, a sampling receiver, and then it would sample, it would go into the threshold decision box. So if we wanted to maximize the SNR, we wanted to come up with the maximum a posteriori estimate of the true bit, we would use the strategy of having our received filter be matched to the received signal. So it's not matched to the transmitted signal, it's matched to the received signal. And the received signal is the convolution of the transmitted signal and the channel impulse response. Or if we look in the frequency domain, we would say that the transfer function of the received filter should be equal to the conjugate of the product of the transmit pulse frequency response times the channel frequency response. So instead of building all these different filters, whether we're doing simulation or analysis, it's often useful to deal with an equivalent system where we group together all of these filters into one equivalent filter. And so the equivalent filter is just the cascade of the 3 filters together. And then we would add our noise after this point. And this is one of the most critical points that people can make a mistake in when simulating system, and that is how to add the noise. If I were simulating the system on the top row, I would use the AWGN command, for instance, in MATLAB, and add a wideband noise. I add wideband noise because that's in the channel what the noise would be well modeled at, but in knowing always that the receiving filter is going to filter this noise. Now, when I've tried to come up with a more convenient way of modeling, it's important that in the second case in the bottom, that when I add the noise, I no longer add broadband noise. What I should now use is an equivalent bandwidth limited noise to accurately assess what's going on in the system. We'll talk a little bit about how you would calculate what noise level you should use post-filtering.